We've talked about how to deal with vectors graphically, how to add them graphically, draw them represented as arrows. But we've also seen how tedious and difficult that can be to get more than just an estimated value. The true power of vectors are in vector components, and that's what we're going to see here. We've seen that for any vector, we can find the sum of any pair of vectors. So for example, here on the left, I have these two vectors. I can use the parallelogram method, and I can find a vector, let's say A and B, that is the sum of these vectors A and B. The same way over here, I could call these two vectors, let's say Cx and Cy, and then I can find a vector that is the sum of these two vectors. The point of this is that if I can say that this vector C is the sum of these two vectors Cx and Cy, then I could also say that any arbitrary vector C could be broken up into these two vectors. If these two vectors added together equal one vector, then any one vector could be thought of as two vectors added together. Specifically, one vector in the x direction and another in the y direction. Why is that helpful? Well, we talked about vectors being parallel and anti-parallel. Parallel vectors are pointing along the same line in the same direction. Anti-parallel vectors are pointing along the same line, but are in opposite directions along that same line. As long as the two vectors are parallel, adding them just means adding their magnitudes. We're back to simple algebra there. If they are anti-parallel, that means they are in opposite directions, and so they'll be canceling each other out, and it's as simple as subtracting them. So we can go back to this idea of breaking every vector up into two vectors. If we break every single vector up into an x and y vector, a horizontal and a vertical vector, then all of the horizontal vectors will all be parallel or anti-parallel with one another, and we can simply add or subtract them. All of the vectors in the y direction will all be parallel or anti-parallel to other y direction vectors, and we can simply add or subtract those as well. For any arbitrary vector A that we assume is in two dimensions in the xy plane, we can express this one vector instead as the sum of two vectors, ax and ay, where ax is purely in the x direction and ay is purely in the y direction. We call this process the decomposition of vector A. We are decomposing this vector into its vector components. In this case, these vectors ax and ay are the vector components of vector A. They are vectors as well, but they are vectors that are purely in the x or y direction and represent the horizontal or vertical portion of the overall vector. In order to find the vector components of a vector, what we can do is, for any arbitrary vector, draw a vertical line through the tip of that vector, draw a horizontal line through the tail of the vector, and we have our two components here. This will be our ax, and this is ay. You also notice that ax and ay are always perpendicular, because the x and y axes are always perpendicular to one another, and so we are always creating a right triangle here, and that will be helpful for us as well. For any arbitrary vector, we can find the x and y components using the same method. For vector A here, I can find the vector components by dropping a vertical line through the tip, a horizontal line through the tail, and here are my x and y vector components. For vector B, pointing up and to the left, the same idea, a vertical line through the tip, a horizontal line through the tail, and I can draw my x and y components. And for this vector C, I can draw a vertical line through the tip, a horizontal line through the tail, and again I have my x and y vector components. Notice here I've been drawing my y component here. Here I've borrowed from a textbook that draws the y component over there, but notice that this vector and this vector have the same magnitude. They point in the same direction, so those are the same vector. It doesn't matter where I locate it on my graph. I like drawing it this way because we have created these right triangles, and we will use these right triangles to find these components of the vectors. One part of this that's a little bit tricky is we are finding vector components. These are ax and ay that are vectors, and they are related to vector A in that they sum up to give us vector A. But part of this, we said that we want to break these vectors up into their component parts, into their horizontal and vertical parts, so that we can have vectors that are all parallel and anti-parallel, and we can return to something more like the algebra and normal math that we are used to dealing with. So these are still technically vector quantities, so we still haven't fully simplified the problem that we're trying to look at here. The other side of this, too, is that if these vectors are in the x and y direction, then we know what direction they're in because we pick them so that they are horizontal and vertical. So we don't really need the full vector quantity because the direction is implied there by the fact that it's in the x or the y direction. So what we typically look at instead is not the vector components, but rather the components, the x and y components of the vector. So, for example, ax here with no arrow on top is a scalar, it's a number, and this number represents the magnitude of the vector component. So ax, the scalar, the number, is the magnitude, it's the length, it's how far we're going horizontally, and it's the magnitude of ax, the x component vector of the original vector A. So the scalar, this number, gives me the magnitude, the amount. Since it's in the x direction, I know the direction associated with it. The last thing, though, is in the x direction. Technically, there's two ways that I could go. I could go to the left or to the right. And so we will use the sign of the vector, of the component, to determine the direction. This could be positive or negative. Positive means that we're going to the right. Negative means that we're going to the left. In the x direction. And positive means up, and negative means down in the y direction. So we can give ourselves all of that information in the vector using a plus or a minus and just a number, and knowing that it's the x or y components, or knowing which axis we're aligned. Those are still vector quantities. We can just express them in a little simpler way. So we're looking to find these vector quantities, these components, the x and y components related to a vector. We know that a vector, by definition, is defined by a magnitude and a direction. Those are the two pieces of information that are needed to fully define a vector. The direction is defined by an angle, and that angle is measured counterclockwise from the positive x-axis. So, for example, for this vector that you see in the picture, we would measure from horizontally to the right, we would measure counterclockwise, and that would give our angle theta. For right now, we're going to assume that theta is between 0 and 90, that this vector is pointing up and to the right. We'll generalize that in the next slide. The components of vector A I can find by drawing a vertical line through the tip and a horizontal line through the tail. Here are my vector components. And then we said that ax and ay, the scalar quantities without the arrow on top, these quantities here are the lengths of these two vector components that I've drawn in. But notice that ax and ay are also the sides of the right triangle I've produced here. By including a horizontal and a vertical line, I have a right triangle. Ax and ay are the sides. The hypotenuse of the right triangle is the magnitude of the vector. This is important. Make special note of this. The magnitude of the vector is always the hypotenuse, and the magnitude of the vector is always positive. How can we actually find these quantities? We're assuming that we know the magnitude, that we have a number here representing our original measurement. We're assuming we know the direction. We're assuming we know this angle here, and we want to find the x and y components, the lengths of these other two component vectors, which in practice are the sides of this right triangle. Well, we notice here that ax is adjacent to this angle, and so if we're trying to find the side of a right triangle, we can use trigonometry, and we can say that cosine of theta is adjacent over hypotenuse, and the hypotenuse is always the magnitude of the vector, and then I can rearrange that to say that AX would be A cosine of theta. By the same token, AY would be A sine theta. In my class, we use standard form. We always measure the angle starting from the positive x-axis and going counterclockwise. So we may have an angle that is bigger than 0 to 90. That was our original vector, was somewhere over here. Now we're talking about a larger angle. So 120 degrees, well, this would be 90 degrees. 120 degrees would be something like this. I have a length of 5, and my angle here would be 120 degrees. Well, I can still find the components of this vector here by drawing a vertical line through the tip, a horizontal line through the tail. There's my right triangle. Here are my vector components. And here are my x and y components of the vector, which are the magnitudes of these two vector components. And again, we have a right angle there, we have a right triangle, because we always do. In this case, our angle is measured in standard form, counterclockwise from the positive x-axis, but we don't know the angle inside our right triangle, right? If we want to use trigonometry to find these sides of our right triangle, we need an angle inside the right triangle. And so in that case, we have to use a little geometry. We know that this is a straight line, this is 180 degrees, this is 120 degrees, and so we can make the argument that this angle must be 60 degrees there. And so what we could do is we could say here, AX is going to be our magnitude, which in this case was given as 5, times the cosine of the angle, and the angle was the angle inside the triangle, because we're using cosine, we're using trigonometry here, and AY would be the same thing, again using the magnitude of the vector and the angle inside the triangle. That's called the reference angle. Here's the thing though, sine and cosine, if we have the angles inside of a triangle, these angles are always going to be between 0 and 90. Sine and cosine are always going to be positive. So these are always going to be positive amounts representing side lengths of a triangle. But this triangle isn't really a triangle. This is a way of thinking of the components of this vector quantity. And a vector quantity could point in any of the directions. We said that to the right is positive and to the left is negative. We said up is positive and down is negative. And so we need to distinguish the direction of this vector up and to the left compared to the vector that was up and to the right that we saw on the previous slide. And the way that we can do that is by manually inserting a plus or minus for each of our components. In this case, we can look at the x direction. The x direction is pointing to the left, so that's negative. So I'm going to keep a negative sign there. I can look in the y direction. The y direction is upwards, so up is positive, and so I'll keep the positive there. An alternative way to do this is that when you use the angles in standard form, the plus or minus is built in to the definition of the sine or cosine. So if you wish, you can also say the x component would be 5 cosine 120 degrees, and AY would be 5 sine of 120 degrees. In this case, the plus and the minus are built into these quantities. This quantity is negative already, so you end up with the same value here. You don't need a external negative sign here because it's built into the cosine of 120 degrees. This is already a positive value, so it matches what you get there as well. So as long as you use standard form, starting from the positive x-axis and measuring counterclockwise from 0 to 360, this will work. I like teaching this method because it keeps us a little bit closer to the, a closer understanding of what we're looking at, because we're just dealing with a right triangle. We're always going to get positive values no matter what, and then it just makes you stop and think, are these positive or negative? And I find that a good way to find a good check of whether you're doing things correctly. Here, the math or your calculator is doing all the work for you, which maybe will give you the right answer, but you may be lost in the steps, and you may not know where to go next from that. Another way that you may see a vector is you may be given a vector, but you may not have the angle in standard form. So there's a couple ways that you could do that, or you could deal with that. In this case, we have an angle phi, and let's say that this angle phi is maybe 40 degrees. One thing you could say is that you could calculate what the angle of that vector is. This would be 90, and then another 90 gets you 180, and then another 90 after that gets you 270, and then 270 plus another 40 would be 310 degrees. And once you know that, you could find the components using this method. Another way that you could approach this is what we have been talking about, where you draw a vertical line through the tip, a horizontal line through the tail. That gets you your x and y vector components, and then we want to find the x and y components of that vector. In this case, we're told 40 degrees, but we don't know, that's not an angle inside of our triangle, so we don't know, what value to use as a reference angle. But what we do know is that this would be a right angle as well. Regardless of what angle is used to define a vector, it's almost always measured relative to vertical or horizontal, one direction or another. And here you can say, well, this whole angle is 90 degrees, this angle is 40, and so this angle would have to be 50 degrees. And then again, you could find your x and y components. Notice here, x is to the right, so that would be positive. Y is downward, so that would be negative. You could find those values as well. Or finally, if you are given this angle here and you already know one angle in the triangle, what you could do is reverse what we were talking about before. Instead of a vertical line through the tip and a horizontal line through the tail, instead we'll draw a horizontal line through the tip, a vertical line through the tail. Again, we have a right triangle here. Again, we have the vector components of B, and we have the x and y components that we're trying to find. In this case, we would have bx, the x component is across from that angle, and so we would use the sine of 40 degrees, and then by would be the cosine of 40 degrees because it is adjacent, and it's downwards, so that's negative. This quantity would be positive. This is actually the same value as what we talked about before. The other way we were talking about it would say bx would be b cosine of 50 degrees if we did it the original way. And you'll note that cosine of 50 and sine of 40 are actually the same value, and these are all three different ways to find the components of the same vector that we have there. Vectors can point in any direction. We've seen vectors that point in all four quadrants. Again, remember that to the right is positive and to the left is negative when we're looking at x components. Up is positive and down is negative when we're looking at y components. If you use the angle in standard form, measuring from the positive x-axis counterclockwise, from 0 to 360, the positive and negative is built into the sine or cosine function. If you choose to use the reference angle, which the reference angle is the angle measured relative to the closest x-axis, that will always give you a positive number, and you'll have to manually include your own plus or minus values there. So we found that for every that a vector is defined as a magnitude and direction, and that for every magnitude and a direction, there is a x and y component associated with that, a unique pair of x and y components. What that means then is that we could define a vector in terms of x and y components, and that's equivalent to having one magnitude and direction to fully describe one vector. So for example, let's imagine we've got this vector here which is -3, -4. Due to the placing, we know that this is ax and this is ay. And due to the fact that we are using these kind of pointy brackets, we know that this is a vector quantity. It's not a it's not a coordinate point. It is a vector, and we know the x coordinate is first, the y coordinate is second. So -3, -4 means a vector that goes 1, 2, 3 to the left because it's negative, and -4 means we're going to go 4 downwards. 1, 2, 3, 4. And so this is going to be the vector that we are looking at here. Notice here again, my style is to say that the -3 and the -4 mean I'm going to the left and I'm going downwards respectively. But once I draw this, I'm thinking of this as a triangle. This side length is 3. The orientation is negative because if it were positive 3, it would go this way, but I'm dealing with this as a side length of 3 and a side length of 4. And if I want to describe this vector, I could describe this as a magnitude, the length of the vector there, and I would want to know this angle would be the angle of vector A. Here I have a right triangle because my x and y are always perpendicular. These are the sides of the right triangle, so I could find the magnitude. The magnitude is the hypotenuse. In this case, the magnitude of the vector is a hypotenuse, and I can find the length of the hypotenuse using Pythagorean theorem. In this case, 3 squared plus 4 squared would equal a squared, and I could find a squared, or more generally speaking, a, the magnitude of the vector, also expressed as the magnitude of vector A, would be the square root of the squares of my x and y components. I also want to find the direction of the vector. I can't really find this angle here. I can find this angle here, right? I can only use trigonometry to find an angle inside my right triangle. What I like to do, because the way that our inverse functions are defined is also a little bit confusing, I like to just use the magnitudes of these amounts. I just use these numbers, and I don't worry about the negative or positive, which just tells me the orientation. What I can do is say that this angle here is going to have a tangent that is opposite over adjacent. So the tangent of this angle is going to be the y component over the x component, or I could say that angle is going to be the inverse tangent of the y component over the x component. But I just want the amount because I want to avoid the confusing ways that the inverse function works. So I'm going to put absolute value bars here and just use the amount, the 3 and the 4, and not worry about whether these are negative or positive. So if I use only positive values here for inverse tangent, it's going to give me a value of theta between 0 and 90, which is going to represent this angle here. So what that's giving me there is the reference angle. The reference angle is the angle inside that right triangle, and that's always going to fall between 0 and 90 due to the way that inverse tangent is defined. But if I know what this angle is, and I know where my vector is based on the direction it's pointing, here it's pointing this way, I can say this would be 180 plus this reference angle would be the true angle. So I can use that reference angle to find the standard angle, which is measured from the positive x-axis counterclockwise. Here in the notes, I have a brief review of trigonometry so that you can use the sides of a triangle, the angle and the hypotenuse to find the sides of a triangle, or if you know the sides of a triangle, you can use trig to find the hypotenuse and the angle.